Good morning, everybody, and welcome to Faculty Development Program 2020. It is my pleasure to be the part of this FDB program, and this opportunity, I am thankful to Dr. Mrs. Sunitra Rautre. Thank you, madam. Myself is Manoj Nemje, and I am working as a senior principal scientist in Jawaharlal Nehru Aluminum Research Development and Design Center, which is located at Nagpur in Maharashtra state. It is an autonomous body under Ministry of Mines, Government of India. The basic idea of this presentation is to give you information about spent pot lining, or in short, we call SPL. SPL is a hazardous solid waste generated in aluminum industry during the production of metal aluminum by electrolysis process. And in this presentation, I will speak about what is SPL, how it is generated, why it is classified as a hazardous waste material by Central Pollution Control Board, that is CPCB India, and what are the different practices or methods aluminum smelters in India or abroad for its disposal, treatment, and utilization. But before going to the spill generation, first we will see how aluminum is produced on commercial scale in brief. The photograph shown here is the real camera captured image of a typical aluminum smelter courtroom, where aluminum, aluminum is produced by electrolysis at 960 degrees centigrade. The vertical units shown here are arranged in called electrolysis pot or electrolysis cells. And these electrolysis cells are connected to each other in series with reference to current. A typical aluminum smelter operates hundreds of such electrolysis cells for the production of aluminium. The size of each electrolytic cell ranges from 25 meters square to 80 meters square, depend on the capacity of aluminum production plant. Now let's go deeper into the structure of the electrolytic cell. The slide is showing the various views of the electrolytic cell, such as cross-sectional view, front view, side view, and the top view. The cross-sectional view is depicting the complete cross-section of an electrolytic cell, and this electrolytic cell is divisible into two parts. The upper part is called the anodic portion, and the lower part is called the cathodic portion of an electrolytic cell. Anodic portion mainly consists of carbon anodes to carry the electric current into an electrolysis cell and alumina hopper to add alumina regularly in the cryolite. Whereas the cathodic portion mainly consists of outer steel shell to support the various refractory linings to maintain the heat balance and the carbon linings to hold the corrosive cryolite bar and carry the electric current. And we are interested in SPL, that is spin port lining. We concentrate only on the lower portion of the electrolytic cell, that is the cathodic portion. The front view, side view, and the top view of cathodic portion of an electrolytic cells are shown here. The cathodic portion is also called a vessel for holding the molten cryolite, and the construction material used in the construction of cathodic portion or a vessel comprises of 1. Carbon blocks. The topmost layer of the vessel is made up of carbon blocks, and these blocks can be made from the anthracite coke or graphitic or graphitized raw material. The main function of this layer or linings are to provide current and avoid the reaction of corrosive bath with refractory lining. The thickness of the carbon lining may be in the range of 380 millimeter, and it acts as a cathode for carrying current. Second, adjacent to carbon blocks and on the periphery there are silicon carbide refractory bricks to provide support to the carbon blocks. Third, below the carbon blocks there is approximately 145 to 150 millimeter dry bed mix to support the carbon blocks and reduce the heat losses. 4. Below the dry barrier mix, there is approximately 64 millimeter layer of high strength insulation bricks. Fifth, below the high strength insulation bricks are approximately 65 millimeter layer of high steel bricks. And below 6 and below the high steel bricks there is 1 to 2 millimeter layer of aluminum powder. And 7. Lastly, all these linings are arranged in a steel shell and all the carbon blocks are joined together or sealed with a ramming paste to avoid the leakages from the vessel. This type of structure vessel is used for holding the molten electrolyte, maintaining the heat balance of the cell and conducting the current, and can be operated up to 5 to 7 years during the aluminum production. Today, carbon source wearing is regarded as a main limiting factor for life of electrolytic cell. Number of researchers are taking much efforts for the improvement of life of cell and efficiency of an electrolytic spot by improving the properties of carbon cathode material. Before 1922 or in early cells, the entire cathode lining were made from the monolithic gram carbon base. But after 1920, pre-baked carbon blocks were made appearance followed by the several improvements in electrical contacts between carbon, cathode and current collector bars. Today, almost all the industrial carbons are made up of pre-baked carbon blocks with improvement in carbon properties. In early days, the average spot life was approximately 500 days. At present, it is approaching 2000 days and still increasing, mainly as a consequence of significant improvement in cathode material and cathode lining design. Mainly three types of the cathode blocks can be used for the cathode lining, namely anthracite-based graphitic blocks and graphitized blocks. The carbon blocks are manufactured by mixing the raw material such as high purity anthracite coal or graphitic material with pitch and then molded into the required size of blocks. The molded blocks are then baked in kiln to get appropriate properties. The preparation process for the same is shown here. In the anthracite block, none or only part of the filler material is graphitized and the block is baked to a normal baking temperature up to 1200 degrees centigrade. In the graphitic blocks, the aggregate is graphitized, but the block and the binder coke have only been heated to a normal baking temperature, that is up to 1200 degrees centigrade. Graphitized block, the whole block aggregates and binder coke consist of graphitizable material have been heat treated up to a temperature of graphitization, that is up to 2500 to 3000 degrees centigrade. Now, coming to the comparison of different cathode blocks. The performance of the cathode in electrolysis cell depends on the types of blocks and the physical properties associated. The table presented here is displaying the comparison between the various properties of different carbon cathode blocks. For example, if the relative price of anthracite-based cathode block is 1, then the relative price of graphitic carbon cathode block is 1.5 to 1.8 times higher than the anthracite blocks, whereas the price of graphite cathode blocks is 2 to 3 times higher than the anthracite blocks. Similarly, the abrasion resistance of anthracite blocks is excellent compared to the graphitic and graphite blocks. Thermal shock resistance in case of the anthracite-based block is acceptable, whereas it is excellent in case of graphite cathode blocks. Thermal conductivity of anthracite-based block is moderate, whereas it is very high in case of graphite cathode block. Electrical resistance in case of anthracite-based block is high, whereas it is very low in case of graphite cathode block. Crushing strength of anthracite-based block is high, whereas it is low in case of graphite cathode block. And most important property for the life of electrolysis cell is the swelling of the block due to the sodium penetration. And this is adequate in anthracite-based block compared to very low in case of the graphite cathode block. Even though anthracite-based blocks are inferior to graphite blocks, anthracite-based blocks are still widely used due to the less in cost, but with the continuous search for improvement in efficiency, productivity, and the life of cell, they are no longer dominating the market. The superior electrical conductivity as well as the resistance to the thermal shock and sodium swelling makes the graphitic and graphite carbon cathode blocks as a preferred choice of modern high amperage cell. Until now, we have seen the structure of the vessel and various properties associated with the carbon linings or carbon cathode of electrolysis cell. Now we will see what is SPL and how it is generated. During the electrolysis process, direct current is conducted into the melt through pre-baked carbon anode to electrolyte the dissolved alumina. In the electrolysis process, the carbon anode is consumed as per the chemical given. That is, alumina reacted with carbon to produce metal aluminium and carbon dioxide gas. Opposite to the carbon anode, the carbon cathode does not participate in any reaction and hence does not get consumed and remains intact in operation for a longer period of time. But over a period of electrolysis spot operation, the carbon lining gradually deteriorates due to the penetration of elemental sodium and liquid bark material into the pores of carbon linings. And this results into the loss of integrity of the carbon lining. The
ஏய்
pore will
அப்படியே ஆண்ட்ராய்டு இருக்குதுடி வரமாட்டேங்குது ஒண்ணுமே.
or the
இல்லடி
speed
இதுல கீபோர்ட காணோம்.
is or
கீபோர்டு
metal or electrolytes from electrolysis cell. And when pot gets filled, the pot is emptied and cooled down and remove the existing line to reuse the steel shell by relining the pot with a fresh lining. And this removed lining material is called SPL or spent pot lining. It is estimated that worldwide, on an average, 3 to 5% of SPL is generated during the production of aluminium by electrolysis process. In India also, on an average, 3 to 5% of SPL is generated each year, and it consists of about 50 to 60% carbon material, and we call it as first cut SPL, and 40 to 50% refractory material and called second cut SPL. These SPL are highly inhomogeneous in nature due to the life of cell, and level of cyanide and fluoride vary from pot to pot and within the pot. The total SPL generation in India is estimated as The total aluminum production in India is about 3.392 million tons per year. Therefore, about 1.35 lakh tons of SPL is generated in India, which is calculated at the rate of 4%, which is a huge amount and requires special attention for storage or disposal due to the significant quantity of hazardous as well as the water leachable material. Now we will see why SPL is hazardous and classified as hazardous waste of class A by Central Pollution Control Board, that is CPCB India. If we look at the table carefully, we can see the first cut SPL or the carbon portion is rich in carbon value, whereas the second cut SPL is rich in refractory value, that is silica and alumina. Apart from this, it also contains the leachable fluoride and leachable cyanide. The leachable fluoride present in first cut SPL of 2 to 5% and leachable cyanide are in the range of 100 to 2000 ppm, and this makes SPL hazardous because as per the CPCB guidelines or definition, any waste which contain the leachable cyanide more than 20 mg per liter or 20 ppm by TCLP method is a hazardous waste under class A category, or any waste which contain leachable fluoride more than 180 mg per liter or 180 ppm by STLC method is a hazardous waste under class A category. And SPL contains both leachable cyanide and fluoride material above the permissible limit assigned by CPCB. Hence, SPL is classified as a hazardous waste by CPCB under Class A and requires special handling. Similarly, in USA, the Environmental Protection Agency, that is EPA, has limited their leachable cyanide limit to less than 30 ppm and total cyanide limit to less than 600 ppm for hazardous waste. Apart from the leachable cyanide and leachable fluoride, SPL also contains traces of the metallic aluminum particles, penetrated sodium, aluminum carbide, and aluminum nitride. And all these elements or compounds, when come in contact with moisture or water, it produces explosive and poisonous gas. For example, aluminum particle, when reacted with water or moisture, it will produce ammonia and hydrogen gas. Similarly, sodium, when come in contact with moisture or water, it will produce sodium hydroxide and hydrogen gas. Similarly, aluminum carbide, when come in contact with moisture or water, it will produce methane gas and lastly, aluminum nitride, when come in contact with the moisture or water, it will produce ammonia and aluminum hydroxide. And evaluation of hydrogen and methane makes SPL potentially explosive. On 19th March 1919, a ship carrying SPL exploded in Port Alfred, Quebec, Canada, killing 2 people and causing $30 million damage to the company. Therefore, a poisonous and potentially explosive properties of SPL make it necessary to use a special precaution in order to transport it from smelter to a treatment site or for safe storage. Now, we will see what are the different processes available for disposal, treatment, and utilization of SPL worldwide. Number of scientists and technologists work on SPL treatment and many processes and patents for treatment of SPL have been published. Some processes have got as far as trial production but were then stopped due to the economical constraint or technical difficulties. In this presentation, we will only discuss only those methods which are in use on the pilot scale or which are potentially new methods. Different practices available in India or worldwide for disposal, treatment, and utilization of SPL are 1. The landfilling of SPL. The second practice is use of SPL in other industries. The third available practice is the pyrometallurgical process for treatment of SPL, and the fourth is the aqueous process for treatment of SPL. And we will discuss this in more details in the coming slide. Now come to the landfilling option for SPL disposal. Landfilling without the treatment is supposed to be the easiest and economical method for disposing of SPL. Therefore, earlier, as per the literature, more than 50% of SPL producers worldwide were using this option of landfilling without any special treatment, which causes the bad effect on the environment. Therefore, legislation come into the existence for the landfilling of SPL. Different countries have different rules for landfilling of SPL, but the minimum requirement today is the storage of untreated SPL should be in a building or a covered pit with a non-permeable base to prevent the fluoride cyanide poisoning of drinking water from an earlier non-covered SPL site. It is also required to drill under the landfill and pump up the runoff waters for cleaning purpose. Today, most of the countries have banned on the disposal of SPL in landfilling. Apart from the environmental issue, the major disadvantage of landfilling of SPL is losing of high gross calorific value carbon along with the sodium and fluoride, which could be extracted from SPL as a value added. The another process for disposal of SPL is use of SPL in other industries. For example, the use of SPL in cement industry. The researchers found that the addition of 0.2% SPL to the cement has been the most successful use of SPL in other industries. And the process for the same is shown in figure. Here, the SPL is mixed with the cement composition and treated as usual. So in this, the carbon part of SPL, which has high calorific value and can be used as a fuel substitute when mixed with the coal. The refractory part of SPL is a source of SiO2 and Al2O3 for cement. The fluoride which are present in the SPL are beneficial to the clinker reaction as the cement processes may run at a slightly lower temperature, and the cyanide which are present in the SPL are destroyed at the cement process temperature. But the addition of SPL to the cement is carried out in France, Russia, Brazil, and South Africa. But nowadays, most of the cement industries stop addition of SPL due to the presence of sodium in SPL. Some cement factories want to produce the low sodium cement and may not want to add extra sodium. Presence of aluminum particles in SPL are deleterious in the finished cement, and there is a variation of SPL composition because SPL is highly inhomogeneous in nature, and there is also some uncertainty in the industry about the long-term effect of SPL on their process or the equipment. The another method for disposal of SPL in other industries is the use of SPL in steel industries. Selco Eco Industries in Italy has used first cut SPL as an additive in steel making. The flowsheet of the same is shown here. During the process, they added the steel scrap along with the coal, lime, and carbon portion of SPL and they found that the fluoride present in the first cut SPL improved the slag formation in molten metal. Therefore, they decided to add SPL as a substitute for calcium fluoride addition. The use of SPL in steel making has been tried in Russia, China, United States, and Brazil, but the present amounts treated are believed to be small. The problems are variability in composition and sizing of SPL. The another method for disposal of SPL is the pyrometallurgical process for treatment of SPL. For example, Reynolds process. The Reynolds, later called Alcoa, has developed a detoxification process where a blend of pre-sized SPL, limestone, and anti-agglomerating agent are calcined in a rotary kiln at about 1000 degrees centigrade using a natural gas as a heat source. The concept of the process was that the limestone, that is calcium oxide, will convert the fluoride present in SPL to calcium chloride, which is insoluble in nature. And at the high temperature, the cyanide present in the SPL will be destroyed during the process. The Renault installed the pilot plant with the installed capacity of 1,09,000 tons per year and processed the SPL. The product of the process was delisted by EPA, that is Environmental Protection Agency USA, as a hazardous waste in 1991. But the delisting was repealed in 1997 and it is listed as hazardous waste. The reason was the real leachability of fluoride was higher than the demonstrated by the used American test. The test used one single leaching for 18 hours with acetic acid, and this test gave an unrealistic low leachability due to the buffering of alkaline SPL. The French test, which used distilled water for 3 consecutive leaching for 16 hours, gives a much higher leachability of fluoride. In the lack of better process, the Reynolds process with the controlled landfilling is still in operation at hazardous waste site. The next pyrometallurgical process for disposal of SPL is the alkene process. The flowsheet of the alkene process is shown here. The alkene has developed a smelting process where crushed and screened SPL, quartz, and iron ores are charged to an electric smelting furnace. The product of the process are pig iron and slag. The molten slag can be reacted with the steam to produce aluminum chloride, which is a necessary raw material for aluminum electrolysis. The process was tried in a full-size smelting furnace, but has now been stopped due to the economics and technical difficulties. The company Tetronics UK has announced that they have a robust plasma treatment for spent pot lining. It is a single stage with minimum pre-treatment. They will recover chloride and energy using the calorific value of carbon in the process. The remaining waste is then converted into inert non-hazardous certified material. They propose to carry out the process at the smelter to avoid the expensive transportation. The plasma process with the vacuum distillation at 1300 degrees centigrade and vaporization of fluoride is also under development in China, but it is also looking cost intensive with operational difficulties. Until now, we have seen the three various techniques for disposal, treatment, and utilization of SPL, such as controlled disposal of SPL in landfilling, utilization of SPL for other industries, and pyrometallurgical process for treatment of SPL. Now we will see the aqueous process for treatment of SPL. First is Alcan, LCL, and L process. The Alcan, now Rio Tinto, has developed the process so-called LCL and L process, that is low caustic leaching and liming process. The various steps involved in the process are shown here in the flowchart. The first step is handling and storage of SPL in a container. The next step is the grinding of SPL to less than 300 micron by an air-swept autogenous mill with air classification and screening to a ground SPL storage. The wet sector consists of leaching step, first leaching with water to extract the soluble fluoride and most of the cyanides, followed by a low caustic to extract the remaining cyanide and fluoride. The next step is the filtration of carbon and insoluble. The next step is, and in the next step, the filtrate is treated in pressurized reactor at 180 degrees centigrade to destroy the cyanides. The liquor after cyanide destruction is concentrated by evaporation and sodium fluoride is precipitated out. The remaining liquor is used in the adjacent Bayer plant. The sodium fluoride may be converted to the less leachable calcium fluoride by reaction with lime. Dalcam has started the Foilic plant in 2008 and reached full capacity in 2014 with the treatment of 80,000 ton SPL per year, and the final product contains 5 times fewer total fluoride and sodium, which allows higher dosage of SPL if added to the cement production. The carbon has a high calorific value, but due to higher economics and technical difficulties, the Randall Environmental Consulting Agency Australia clearly indicated in their final National Summary Report October 2016. The quote is that although this process is at commercial scale, it is still in an R&D phase and not likely to be able to service Australian smelt. So, even though the processes are available for treatment and utilization of SPL, some lacunae are there. Therefore, SPL producers are still looking for for better process for their SPL utilization. So, looking at the pros and cons of various available processes in terms of capital cost or operational cost and technical difficulties, JNARDDC has developed its own simple and economical process for treatment of first cut SPL, along with National Aluminium Company, that is Nalco India, and Vedanta Aluminium Company. So, we will discuss this in more details in coming slides. Why we have selected first cut SPL only? Because deep study on the analysis of first cut SPL and second cut SPL shows that high level of cyanides and fluorides are associated in first cut SPL, that is carbon portion, compared to the refractory portion. And therefore, the study is carried out on first cut SPL only. So, during the development of the process, a detailed lab scale as well as the bench scale studies were carried out at JNARDDC using the first cut SPL of Indian smelter plant. The study comprises of detoxification of first cut SPL, recovery of caustic, that is NaOH, and fluoride, that is calcium fluoride by leaching process, and the recovery of carbon value with high gross calorific value. And during the detoxification study of first cut SPL, a detailed detoxification study of first cut SPL is carried out in a rotary kiln or rotary furnace. During the study, destruction of leachable as well as the non-leachable cyanide were carried out by heating the sample at various temperature. A plot between the heat treatment temperature and percentage cyanide, that is leachable and non-leachable, destructed indicated that more than 98% of leachable cyanide is destructed at a temperature range of 400 to 450 degrees centigrade. And it is also found that non-leachable cyanide is also get destructed as the temperature increases beyond 450 degrees centigrade. And during the recovery study of leachable sodium and fluoride, the extraction study is carried out in a stir tank reactor. During the recovery study, the heat-treated spill sample were leached in water in the solid-liquid ratio of 1:10, and caustic concentration of leachate continuously increased by repeated recycling of the filtrate. The final leachate or filtrate containing the soluble fluoride is separated out by adding lime and converting to the insoluble salt of calcium fluoride. During the process, the caustic concentration achieved up to 110 to 150 gram per liter. So, based on our lab scale and bench scale study, I am summarizing the inputs and outputs of the process are shown in this diagram. Here the input to the process are first cut SPL, second input is some amount of heat to rise the temperature of SPL to 400 degrees centigrade. The third input is 1:10 amount of water to leach out leachable sodium and fluoride, and last input to the process is some amount of lime to separate out the leachable fluoride as an insoluble salt of calcium, that is calcium fluoride. The outputs of the process, which are characterized by TCLP and STLC method and gross calorific value analysis, are washed, non-hazardous, and improve gross calorific value carbon. Here I am saying non-hazardous because the leachable cyanide and leachable fluoride present in treated SPL is much below the permissible limit assigned by CPCB. The other output of the process is recycled caustic liquor with concentration in the range of 110 to 150 G, and this will depend on the ratio of leachable sodium to leachable fluoride present in the first cut SPL. And the last output of the process is calcium fluoride with a purity of near about 65 to 70%. Based on the various detailed parameters obtained during the lab scale and bench scale experiments, we designed a pilot scale plant of 5 ton per day capacity, which is a semi-continuous plant, and the schematic of the semi-continuous pilot plant for SPL treatment is shown here. Plant is mainly comprises of SPL side reduction system or section where the SPL is crushed to a size of less than 5 millimeter size by suitable primary and secondary impact mills. The heat treatment section comprises of a rotary kiln where the SPL is heat treated to 400 degrees centigrade and heat treated sample is stored to silo after recovery of heat. The cooled sample from the silo then continuously transferred to a leaching section where it is leached with water in screw conveyor type system. The leached sample then transferred to washing conveyor to remove the adsorbed sodium and the fluoride. The process looks to be very simple, economical, and technically feasible compared to the other process available in the literature and which are working on the pilot scale. And apart from this economics, it is not producing any other waste, or we can say it is a zero waste process. Now, coming to the observation and conclusion of JNARD disease process for treatment of Hashkat SPL, it is observed that almost all or more than 98% of leachable cyanide get destroyed from first cut SPL by heat treatment. The insoluble cyanide can also be destroyed if treatment is carried out at elevated temperature. The maximum extraction of soluble sodium and fluoride into the filtrate can be done by leaching and washing heat-treated first cut SPL sample. The sodium concentration in the filtrate can be increased by repeated recycling of leach filtrate. There is the percentage carbon in the wash residue enhances due to the removal of the soluble material, and there is the enhancement in the gross calorific value of SPL or treated SPL compared to the original SPL, as you can see in the attached report. The gross calorific value of the original SPL is about 5,200 kilocalorie per kg, which it enhances to 6,000 kilocalorie per kg. The untreated SPL is more corrosive while burning, whereas no remarkable corrosion was seen in the container when wash residue was burned in the furnace. The TCLP analysis of the final products showed that the hazardous elements which are present in the SPL or in the treated SPL are much below the permissible limit given by CPCB in their Management, Handling and Transboundary Movement Rule 2015 for cyanide and fluoride. Hence, it is concluded that the final products are non-hazardous in nature. And at last, I want to tell you about that based on the wide experience in SPL characterization and process development, CPCB recognized us as a technical expert for Aluminum Industry Hazardous Waste Management Board. और इसी के साथ अंत में मैं आप सभी को धन्यवाद देता हूं कि आपने धैर्य के साथ प्रेजेंटेशन को सुना और बैठे रहे। अगर आपको कुछ क्वेरीज है या आप स्किल के बारे में कुछ और ज़्यादा जानने की इच्छुक है तो आप हमें हमारे ईमेल या फ़ोन पर संपर्क कर सकते हैं। हमारा ईमेल है mantukni@gmail.com और फ़ोन नंबर है 9921294236। और इसी के साथ मैं आपसे विदा लेता हूँ। धन्यवाद। थैंक यू।
So the participants, the session is now open for discussion. So anybody having any query, you can ask.
Good morning, sir. Am I audible?
Yes, sir. Samir sir.
Good morning, sir. Sir, your process is in now pilot stage. So presently, which process is used by aluminum plants to destroy that waste or treat the waste?
Nimje, sir.
Good morning.
Mr. Manoj Kumar Nimje, sir, please, somebody is asking. Please, sir. So, sir, just wait. I think I'm contacting over phone. Just wait, sir.
ये अच्छा अच्छा, ठीक है, अभी आ रहा है ना?
हाँ, sir.
हाँ ठीक। हाँ बोलिए सर।
हाँ, good morning, sir.
गुड मॉर्निंग, गुड मॉर्निंग।
Sir, now your present research, it is on
या
pilot
या
scale. So
या
presently on means that aluminum plants are which using which method for treatment of their waste?
अभी तो वो जनरली यूज करते हैं लैंड डिस्पोजल। लैंड डिस्पोजल यानी वो एक शेड बना लेते हैं नॉन परमेएबल में बेस का, और वो शेड में वो पूरा अपना सैंपल्स रखते हैं जो
Okay,
भी
मतलब जो
एक्सपेल वो
hazardous
शेड में
waste
रखते हैं।
level के हिसाब से.
हाँ, हजार्डस वेस्ट के हिसाब से
Okay,
जो भी
thank you.
उन्होंने रूल्स रेगुलेशन दिए सीपीसीबी ने, उसके हिसाब से वो पूरा शेड में रखते हैं।
Okay, thank you.
I have one question, sir. Good morning.
या प्लीज।
Actually, in this presentation, I have seen that cyanide is a major issue. Okay, so is there any means by which cyanide extraction can be done and then cyanide can be reused?
No, the cyanide is in the very means minimum quantity, that is in ppm level.
Yeah, in ppm level only, but it is
Yeah,
causing a major problem, right?
yeah.
So no projects have been done so that
नहीं
cyanide
जनरल
can be
नहीं
extracted and
नहीं
reused.
या क्योंकि अगर अपन आयन एक्सचेंज प्रोसेस भी अगर यूज करते हैं इतना साइनाइड रिमूव नहीं होगा,
Okay,
बिकॉज
okay,
देयर आर लिमिटेशंस। तो
okay,
बेस्ट मेथड क्या है, उसको हीट ट्रीट कर दो
okay.
400 डिग्री सेंटीग्रेड। क्योंकि हमें क्या कॉस्टिंग, हम अभी कमर्शियल प्रोसेस में जा रहे हैं ना, तो सबसे
हाँ
इम्पोर्टेंट तो हमारा कॉस्टिंग यानी
हाँ हाँ
इकोनॉमिक्स।
हाँ
इसलिए जनरली ये मेथड थोड़ा इकोनॉमिकल दिखता है। अगर हम दूसरा प्रोसेस यूज करते हैं तो वो थोड़ा इकोनॉमिक्स नहीं होता, तो इकोनॉमिक्स नहीं आने से फिर उसको कोई यूज नहीं करेगा, तो हमारा
yeah,
रिसर्च हो जाएगा।
okay,
ठीक
okay,
है, कोई भी कमर्शियल स्केल में डालने के पहले हमारे को सिर्फ उसका इकोनॉमिक्स देखना पड़ता है rather than the research.
okay, okay, sir. Thank you so much.
Okay, okay, thank you, madam.
Any more question?
ಸರ್ ಸರ್ ಹೊಟ್ಟೋದ್ರಾ?
ಹಾ,
ಹೌದಾ? ಅದೇ ನಿಮ್ದು ಒಂಚೂರು ವೆಬ್ಸೈಟ್ಗೆ ಡೀಟೇಲ್ಸ್ ಬೇಕಿತ್ತು, ಪೇಪರ್ ಪಬ್ಲಿಕೇಶನ್ಸ್ದು, ಆಮೇಲೆ ಇದ್ರದ್ದು ಏನದು FDP ಕಾನ್ಫರೆನ್ಸ್ಗಳದು. ಅದಕ್ಕೆ ಅವ್ರು ಕೇಳ್ತಾ ಇದ್ರು, ನಿಮ್ದು ಪರ್ಸನಲ್ ಫೈಲಲ್ಲಿ ಎಷ್ಟಿದೆ ಅಷ್ಟು ಹಾಕಿರ್ಲಾ? ಸರಿ ಸರ್, ಓಕೆ. ಅಲ್ಲ ಪೇಪರ್ ಸರಿ, ಇದ್ರದ್ದು ಇದ್ರದ್ದು FDP ಕಾನ್ಫರೆನ್ಸ್ ಎಲ್ಲ ಕೇಳಿದ್ದಾರೆ.
ಕಾನ್ಫರೆನ್ಸ್ ಅದೇ ಆನ್ಲೈನ್ ಮಾಡಿರೋದಷ್ಟೇ.
Say, anyone wants to ask any question? So, as there is no question from the audience,
Okay.
so thank you very much, sir. Sir, actually, this SPL is a serious issue and need to be addressed properly, and you are doing so much of work in this particular area. Very great work, sir. So thank you, sir. Thank you for your nice presentation and giving such insight to this particular topic. So thanks a lot, sir.
Okay. अब मुझे एक और इन्फॉर्मेशन भी देना है कि अभी अल्कोआ भी शायद हमारे साथ वीसी करेगा ये प्रोसेस के बारे में। शायद उनको ये प्रोसेस थोड़ा पसंद आ गया है, तो अल्कोआ जो कनाडा है वो भी हमारे से वीसी करने वाला है इसके बारे में।
Okay, okay. Thank you, sir. Thanks a lot.